Hey class, this is Mr. Schmidt with our week 17 recap of the power introduction. Okay, so we had a lot of wide-ranging things to cover here today, but luckily it moved fairly quickly. Notice Wednesday we'll be doing grade defense on yield. The answer key for that is already posted on the YouTube channel. Okay, Friday we'll be talking springs, and then we see our next few weeks are laid out before us. We'll have a mini quiz at the end of next week. Then we'll do review, kind of a dead week of no new content, and then we'll have final exams the week after that. Okay, so let's start with some recap of astronomy speaking, what's happened over the last couple of weeks. Okay, so December 21st, why is it the first day of winter? Okay, and to answer that, I went to earthsky.com. They have a pretty, or .org. They have a pretty good explanation of all these things. So first of all, for as long as people have been looking up in the sky, they've noticed that one day a year, the sun is lower in the sky in the northern hemisphere than it is the rest of the year. And then 6 months later, the sun is at the highest point in the sky. And those people in the southern hemisphere notice the same pattern, only the dates are switched, where December 21st, the sun is at its highest peak, and June 21st, the sun is at its lowest peak. So those of us in the northern hemisphere call December 21st the first day of winter because the sun is so low in the sky. And like I said, that was all that was known for a very long time of human history. But in the last couple hundred years, thanks to the work of people like Kepler and Galileo, we now know that as the sun comes to a certain point in space, the axis of the Earth is pointing away from the sun. The northern point of the Earth is pointing away from the sun, and so we get less direct sunlight. So if we looked at that December 21st at 10:02 Universal Time, the sun was directly over Central Africa. Okay, so they were getting direct, intense sunlight. Okay, people in north of the Arctic Circle were not getting any sunlight whatsoever. Okay, so that's why it was so cold up here and why it's so warm down here. In 6 months from now, you're going to see a mirror image of this. Okay, so again, the Earth's axis is tilted in such a way that in the winter, the northern hemisphere, in January, December, the northern axis is tilted away from the sun, and in June, the northern axis is tilted towards the sun. Notice we don't have any one clear directionality to this one versus that first image. Okay, there is no inherent north-south in space, so they can draw it any way they want depending on what they want as their background feature. Okay, but this gives us a point. It also starts to hint at the fact that this is not a perfectly circular orbit. Okay, but it's not a very good drawing in terms of that, because what we see is that the Earth gets closer to the sun at some points in time and farther away from the sun at other points in time. And that is much harder to observe from standing on Earth, and it is much harder to calculate. Okay, so long through human history, we thought the Earth-Sun system was perfect circles. All right, on through Copernicus. Okay, but when we started getting towards Galileo and then finally Kepler, we saw that the orbit was not perfectly circular. If we compare the black line, the circle, to the red line, which is the actual orbit of the Earth, we see that there's one point where it's a little bit closer to the sun and one point where it's a little bit farther away. I say a little bit in terms of astronomy. 5 million kilometers in terms of actual distance. Okay, so keep that in mind as we look at things like all right, so keep that in mind as we look at things like social media. It says, isn't it a miracle that if the Earth was 5 feet different in orbit, life wouldn't exist. Well, no, Earth does oscillate by about 5 million kilometers. And if we were to chart where life could exist, it's a pretty broad range. Now, it's obviously life doesn't exist on Venus or Mars, so there's some range there, and some of it has to do with the Earth's size and its ability to hold an atmosphere. Also has to do with the ability to sustain life and what the things the astronomers and NASA is looking for in other planets and other solar systems is size of the planet, ability to hold an atmosphere, ability to have water, and liquid water are all things that help to sustain life. But the distance from the sun definitely changes, okay? And it can change over time slightly as well. Okay, so if we look at when did we come closest to the sun, that was actually just a couple of days ago. We passed at about 4:50 a.m. Pacific time, we passed the closest point to the sun. Now, the fact that we were not facing towards the sun in the northern hemisphere meant we didn't feel much warmth at all. Okay, so the direction we were facing was far more important than the relative closeness to the sun itself. Okay, so I just wanted to throw that out there. There's a couple interesting astronomy facts that passed our way over break that I wanted to make note of. Okay, but our actual lesson today is about power. Okay, so power in the terms of physics, okay, is going to be what we're going to try to calculate today. And so we're going to be calculating energy and power to solve our problems. Okay, we're going to see 4 physics questions come up today, all of them following the same pattern. Okay, that pattern is using work as a change over time. Okay, so power is the change in work over time, and it's measured in watts, which we're going to see some confusion here. Watts can be abbreviated as W, work can be abbreviated as W. We really have to pay attention to, is that W a unit or is that W a variable? Okay, so this is going to be the one equation we're adding to our list. Okay, power is work over time. Okay, so how much power will I use to run one flight of stairs? So let's take a look at that. All right, so if we're asking how much power will I use to run up one flight of stairs, we're going to use that equation, power is work over time. Then we have to work our way backwards to see what do we need to find out work over time. Well, time is something you can easily measure. You have a device to measure that. Work, there's no device or app that's going to directly give you work. That's something you have to measure other points and calculate out. Okay, so work, we can use a change in energy, or we can use work as force in the same direction or parallel to displacement. So in this case, if work is change in energy, assuming I'm going the same speed, or I start at rest on the stairs and I end up at rest on the stairs, then my change in energy was just going to be my change in potential energy, potential gravitational energy. Okay, so this maps out what we want to do. Okay, and keep in mind, whenever you're doing an assignment, whenever you're doing a lab or assessment, start with that. Say, this is what I'm trying to find. What am I going to need to do to get there? And then come back with your numbers. Okay, so we looked at the conservation of energy. I said assume while I'm at rest at both points, or you could assume they're at constant speed and they don't change. Okay, if we're going to do a lab, it'd actually have you run the stairs and you calculate your speed. Okay, so I found my mass. Let's say I was running the stairs at quite a fast speed, 3 seconds to go up a flight of stairs. Here are my stairs here. Okay, notice mass times gravity, that is a force, and height. So what I need is just the height. This distance does not matter. Okay, so then I do my mass times gravity times height. That gives me my work. Work tells me my change in energy, and then I can do my work over time to get my power in watts. Okay, and like I said before, watts is W, work is W, make sure you're paying attention to context. If I say 1000 W, that means I'm using it as a unit. Say W equals, that means I'm using it as a variable. Okay, so that is how we solve this example right here. All right, so now that we have an answer to this example, we can look back over the equations we've had. So we've had work is the change in energy, as work is force times distance. This is our new one. Power is work divided by time. Okay. Now with that idea of initial energy equals final energy, that becomes the structure that we can build any other equation off of, and we can keep adding complexity to that structure. Now, you're in AP Physics 1, which means we are strictly going to focus on mechanical energy, and we're not going to get much beyond these three right here. We're going to get some circular motion, but we're not going to add too many more types of energy here. Okay, so we have gravitational potential, kinetic energy, and spring potential. Okay, so spring potential is what we're talking about next week. Okay, so those our core that we can do, our E1, can be any combination of those three energies. Okay, but that's not to say that those are the three energies that exist in the universe and that physicists and engineers have to worry about. Okay, there are a lot of other kinds of energies that we could calculate. I want to show you those calculations, but you're not going to be asked to do those on the test. Okay, so we have thermal energy. Okay, so when they say things like ignore friction, this is the stuff we're ignoring. Okay, but once there's friction, then we're starting to turn some of that kinetic energy into heat, into sound, into current, into something else that would then have to be measured and tracked and accounted for. Okay, so thermal energy would be one, electrical energy or electrical current and its energy would be another one. Electric potential is another type of energy, and magnetic potential is another one. So you'll see some interesting videos where if you drop a metal disc down a metal cylinder down a pipe, it's actually going to behave quite interesting as it builds up current and field, an electric field within that pipe, and it's going to start experiencing all sorts of other forces and energies that we haven't accounted for here. Okay, all right, so let's say you were to, you're driving, you apply your brakes, okay, well now you have friction, friction turns to heat, heat can quickly turns into infrared radiation. So you're going to start bleeding off some of that heat in the form of radiant energy, okay? And talk about confusing equations. We said W can be work or W can be watts, depending on your context. Even harder context to read is V can be velocity, V can be volume, or we can have this Greek letter as a measure of frequency. Okay, so we really have to pay attention to context when doing our equations. But again, this is not one we're going to be focusing on here. This is just, I want to highlight the fact that energy comes in many different forms. When we say energy cannot be created or destroyed, it can only change forms. There are a lot of forms out there. There's a lot of ways we can calculate those forms. Okay, the last one I listed here was wave energy. Okay, so that gave you kind of a hint at all the different equations we could pick from. And then we could look at all the different just line items here. Okay, so we're really only focusing on the three of them: the kinetic, mechanical, the gravitational potential, and the spring potential. But like I said, we have a lot of them here. Okay, nuclear potential, I've never, like even in my undergraduate work, I never really had a chance to dive into measuring and using nuclear energy. Okay, that's just expensive, complicated, dangerous, okay, not something that was going to be relevant or necessary for my training. So it never crossed my path. I did do some math around it, but never hands-on equations or experiments. Okay, chemical potential, you use that all the time when you're plugging in a battery, when you're running a chemical equation. There's all sorts of different ways. When you're burning something, you can deal with chemical potential quite often. Okay, so if we take those and split them into the two big categories, we see that either it's stored or it's in motion. Okay, so we almost exclusively talk about gravitational potential, and we could talk about stored mechanical, which is going to be our springs. Okay, but you could also store it in the nucleus, or you can store it in the chemical bonds. Okay, once things start moving, you can talk about all the particles moving together, which is our kinetic energy. Okay, or you can talk about them moving individually across against each other, which is our thermal energy, and then it is moving with waves and with light and with radiation and all those pieces as well. Okay, so again, we're only really focusing on a few, but that is why we show our work, why we learn these processes, is because now we can start hanging more and more ideas off of this central truth that energy cannot be created or destroyed. It only changes forms. Okay, so I have an exam just coming back to you. Love a little Schrodinger's joke whenever you can get it. Okay, so your test score is both good and bad until you look at it. All right, so we have an assignment here. Okay, I appreciate this specific assignment because A, it follows a nice simple structure that we just did in our example. I also appreciate it because it has 23 squirrels doing push-ups. And so you really have to think about what is displacement, what is force in terms of these 23 squirrels doing 5-centimeter push-ups. Okay, so that is your assignment. I think most people got that done in class. I'll be posting that answer key here shortly. Okay, and then the other thing you need to do going into storm time this week is to reflect on your test. So if you got something right on the new test, but you got it wrong on an old test, show those to me, and then tell me why those two account for each other. Okay, so for example, we had the question number 1 on the test was a graph, velocity time graph. Well, if now you understand how velocity time graphs account for displacement and acceleration, say, hey, here's where I did not understand velocity time graphs, but now I do kind of have points. That's what Wednesday is all about. So bring in all your content, try to look at it, reflect on it, and come ready to ask me questions or lobby for points, okay? And keep in mind, this is also what we're gonna be able to do after the final exam in a couple of weeks. You'll, again, be able to use any question and apply it against any older question as you demonstrate mastery of a standard. Okay, so with that, the rest of the time was spent doing your work, and I bid you all a good day, and I will see you in class soon.